Welcome back for this is part 2 of a right Riemann sum example. We had our linear function 3x minus 4 on the closed interval 2 to 5, and we had already calculated the summation notation for the right Riemann sum. And to remind you of that, we had calculated delta x is 3 over n. We had calculated the grid points xk, 2 plus 3k over n, and eventually we wrote the summation notation for the sum of the areas of the rectangles approximating the area bounded by the curve. So we had the sum k equals 1 to n, 3 times x sub k minus 4 times delta x, or 3 times that sum minus 4, that quantity, times 3 over n. Okay. And in a moment, we're going to simplify this expression. We're going to calculate some closed forms of the sums, and then apply the limit to find the actual area under the curve. And I thought we'd just take a moment and review that there are closed formulas for certain familiar sums. So let's say we're going to add up 1 plus 1 plus 1 n times. Well, we know that's going to be a sum of n. More generally, if we had a constant c, and we're going to add c plus itself n times, we could more simply just take c times n, and this product would be the equivalent to that sum. And in class, we've talked about the sum of consecutive integers. So here the counter is k, and it's going to tick off 1 plus 2 plus 3 plus 4 all the way up to n. And if we add up those n consecutive integers, we will get a total dependent on n, which would be n times n plus 1 all over 2. And I think that's all we're going to need for our example today. But there are closed forms for any power of k, where k is that counter. Okay, let's move along. Okay. So this is where we left part 1. We had the summation notation for the right Riemann sum, and we want to simplify that. Excuse me, I'm going to move our camera back. I think I moved somehow. Okay, so we're looking at that summation. And maybe first I might distribute that 3 over n. We could just factor 3 over n outside of the summation before we apply the limit, but let's just keep everything together right now. So we're going to take 3 over n times this product. That will give me 9 over n times 2 plus 3k over n. So that was 3 over n times the first term. And then we'll subtract 3 over n times 4. And that entire expression is still under. Or we're taking the sum of that expression. Alright, let's simplify a little bit more. Let's distribute the 9 over n through the parentheses to get 18 over n plus 27k over n squared. And then we need to remember to subtract off 12 over n. And continuing to simplify, we'll have k equals 1 to n. We do have like terms here. 6 over n plus 27k over n squared. Great. Okay, now we can, because we're just adding a bunch of sums, we can reassociate. And there's a property of summation that says we can sum up the elements of the first term and then add to that the sum k equals 1 to n, the elements of the second term, n squared. And then since k is our counter, our index, and n is a constant, we can actually factor out the 1 over n and not change the sum, leave the 6, and we can factor out the 27 over n squared and leave the k inside, of course, because that's cannot be taken outside the summation. And this is the point where we can apply those summation formulas we looked at previously and get a closed form for this Riemann sum. Okay. So if we're adding 6 plus itself n times, that total will just be the product 6 times n. And if we're adding up consecutive integers, 1 plus 2 plus 3 all the way up to n, that total will be n times n plus 1 all over 2. Okay, and that's where we will continue. And we've been asked to find the limit as n goes to infinity of what we've found as the right Riemann sum. Okay, so we're going to take the limit as n goes to infinity of 6n over n, this product up here, plus 27 n times n plus 1 all over 2n squared. Okay, now since n is going to infinity, n cannot be 0. And so n divided by n will just be 1, and we have the constant 6. The limit of a constant is just that constant. But we need to still find the limit of that second term. Now upon inspection, we can see that we have a quadratic polynomial in n over a quadratic. If we don't see that right away, we can multiply through. N times n is n squared, and n times 1. And if we still don't see it right away, we can multiply through the parentheses, and we have this degree 2 polynomial up top. So this limit exists because the degree of the polynomial on top is the same as the degree of the polynomial on the bottom, and the limit is going to end up being the ratio of the leading coefficients, 27 over 2. And we have a closed form. Let's make sure I did that. Yes. 27 over 2 is 13.5. Let me get that back on the screen there. And so our final answer should be the exact area of this trapezoid. And with a quick check, and I'll leave you with this thought. The area of this little rectangle here was 3 times 2, or 6. And the area of this triangle here was 1/2 the base, 3, times the height, 9. And check it out. Here we have our 13.5, I believe, half of 27. And here we have our area of 6, and that's our area 19.5. Thank you for your attention and watching this video.